Welcome. Today, we're going to dig into this really cool story about self-reliance, right from the heart of the software world. It's all about how the Linux kernel, one of the most complex software projects on the entire planet, actually uses its own inventions to solve its own biggest problems. Look, you've heard this 1,000 times, right? Containers, Docker, Kubernetes, these things are the bedrock of the modern internet. They're running basically everything, from your Netflix queue to giant cloud data centers. I mean, they're literally everywhere, and they've totally changed the game for building software.
But let's get real for a second. Past all the hype, what is a container? Is it some kind of tiny little computer? Is it magic? Well, not exactly. The answer is actually way more interesting, and it's hiding deep inside the Linux kernel itself.
So to really understand this whole story, we have to go right to the source. We're going to peel back the layers and look at the fundamental building blocks inside the kernel that make all this modern container stuff even possible.
That's it. It's not magic at all. This whole multi-billion-dollar industry, this entire ecosystem, it all boils down to two really clever and powerful ideas that have been in the Linux kernel for years. So let's break them down.
Okay, so the first hero of our story is something called namespaces. The easiest way to think about a namespace is that it puts a set of blinders on a computer process. A process running inside its own little namespace can only see itself. It thinks it's process ID number 1, the king of the castle. It has absolutely no idea that other processes are even running on the same machine. It gets its own private little universe to live in.
And our second hero? That would be control groups, or as most people call them, cgroups. Now, if namespaces control what a process can see, cgroups control what a process can use. This is like the resource police. You can tell a cgroup, hey, any process in this group can only use 1 CPU core and maybe 500 megs of RAM. That's it. Cut them off. It's like putting a hard budget on what they're allowed to spend.
So you see, they're really two sides of the same coin. Namespaces give a process its own private world, what it can see, and cgroups give that same process a strict budget for what it can use inside that world. One is about isolation, the other is about limits. You put them together and bingo, that's the foundation of a container.
Okay, so the kernel gives us these incredible tools. Awesome. But now, let's flip the script and talk about the kernel's own massive problem. You have to remember, this is one of the biggest, most complicated open source projects that has ever existed. And actually building it, compiling it, well, that is a huge challenge. Now, if you've ever compiled a kernel for your own computer, you've probably seen something like this. And it looks so simple, doesn't it? Just download the code, pick some options, and type make. But trust me, that simplicity is hiding a mountain of complexity. And here's where the real trouble starts. The Linux kernel doesn't just run on your laptop. It runs on everything. Your phone, your smart fridge, your car, those massive IBM mainframes, you name it. And obviously, you can't just have one of each of those machines sitting around to build the software. You have to cross-compile. And just look at this list. This is just scratching the surface. Each of these is a totally different world, different instructions, different rules. It's just a staggering amount of hardware diversity that the kernel has to support. It's kind of wild. Now, to build for, let's say, an ARM chip on your regular laptop, you need a special set of tools, a compiler, a linker, the whole shebang. We call that a toolchain. To build for a PowerPC, you need a different toolchain. And trying to install all of these different toolchains on your one development machine, it's a disaster, a total dependency nightmare. So how do the kernel developers actually solve this? How do they manage this insane level of complexity without losing their minds? Well, and this is the really beautiful part of the story, they use the kernel's own tools to solve the kernel's problem. They use a containerized build. The idea is brilliant in its simplicity. For every different type of computer you want to build for, you create a perfect, clean, isolated little environment that has exactly the right tools and libraries for that one job, and nothing else. No mess, no conflicts.
And what's the secret weapon they use to create these little isolated worlds?
It's often a really clever utility called debootstrap. It's a tool that can basically install a bare-bones operating system into any old folder you point it at. So this is how it works in practice. First, you just create a big, empty file to act as a pretend hard drive. Then you format it, you mount it, and then you point debootstrap at that empty space. The tool just goes to work and installs a complete minimal operating system with the exact compiler toolchain you need right into that folder. And just like that, you've got a self-contained environment all ready to go. Think of it like this. Every single build gets its own perfect, specialized workshop. The workshop for building ARM code has all the ARM tools laid out just so. The S390 workshop has all the S390 tools. And
Most importantly, they're completely walled off from each other, so there's no way they can interfere with one another.
And this approach just completely solves all those problems we talked about before. Those toolchain conflicts? Gone, because everything's isolated. The classic, well, it works on my machine bug? Gone, because every build is perfectly reproducible. That ridiculously complex setup? Solved. You just have a bunch of simple, pre-configured environments. It's clean.
And this is where it all comes full circle. It's so cool. The kernel provides namespaces and cgroups for isolation. The kernel developers then use that exact isolation to create a container with the perfect build tools inside. And then that container, which only exists because of the kernel's features, is used to build the kernel itself. The creator is literally being saved by its own creation.
It's such a powerful idea, this pattern of using a system's own output to improve itself. And it really leaves you with a final question to chew on. What other huge, complex problems are we trying to solve with outside tools when maybe, just maybe, the most elegant solution is already hiding inside the system itself? Thanks for watching.